Hello everyone, I am Claudio Mancinelli from the University of Genoa, and in this talk I will describe an algorithm to compute the cut locus on discrete surfaces. This work is with Marco Livesu from the CNR and Enrico Puppo from the University of Genoa. The cut locus of a point x on a manifold can be defined either as the closure of the set of points where a shortest cure from x fails to be unique, or equivalently, as the closure of the set of points where dx fails to be differentiable, where with dx we are denoting the mapping that associates to every point on the manifold its geodesic distance from the fixed source x. In the image in the slide, for example, dx is visualized through its map and isolines. And note that since there are two minimizing geodesics connecting x and y, in this case we have that y belongs to the cut locus of x and vice versa. However, from now on, x will be fixed and we will refer to it as the point which we are computing the cut locus. Note that the non-differentiability of the x at the cut locus implies that its gradient, sampled at the vertices of the mesh, for example, somehow breaks while approaching the cut locus, and we will exploit this fact later on. Moreover, the two definitions we have just given suggest that the cut locus of x encodes some precious information about, for example, the unicity of a given shortest curve starting from x or the differentiability of the x. Such information are quite important in many algorithms in geometric processing, machine learning, and in the optimal transport theory. Nevertheless, there are not so many works in the literature addressing the problem of computing the cut locus of a point on a surface. The problem with the algorithms listed in the slide is that they are either slow, in the sense that it takes minutes or hours to compute the cut locus of a point, or they are targeted for specific types of surfaces, for example, homogeneous surfaces or convex ones, or they suffer of both of these limitations. Our main contribution is an algorithm that computes the cut locus of a point in seconds on arbitrary shapes and large meshes. Every step of our algorithm finds its theoretical foundation in one of these four properties. The first one states that the Riemannian Laplacian of the distance function goes to minus infinity at the cut locus. The second property states that if x is a point on a surface, then its cut locus is a finite graph, and it has the local structure of a tree. The third one states that the cut locus of x and the manifold have the same homology, while the last one states that the cut locus of x is smooth at all regular points, where with regular points we mean all those points on the cut locus which can be connected to x with more than one geodesic. Let us start by analyzing the first one of these four properties. To do this, we choose our point x on the torus and we compute the geodesic distance field dx. In the slide, x is represented with a yellow dot, and we are visualizing dx through its map and isolines as before. So we compute the Laplacian of dx, and we note that the vertices at which such Laplacian reaches its minimum values outline somehow a region on the torus, and such region is quite similar to the cut locus we would like to compute. However, note that there are some valleys that are less visible than others. And for example, it is the case of the valley relative to the inner loop of the cut locus. In a moment, we will show how this may affect the computation of the cut locus with our algorithm. So we would like to exploit the behavior of the Laplacian we have just seen to build a spanning tree that somehow is aligned with the values of the Laplacian. This makes perfectly sense since we know by property 2 that the cut locus is locally a tree. So to do that, we set the root of our tree to the farthest point from the source, which on a compact manifold surely belong to the cut locus. And then we use a priority queue to determine in which order a vertex should be added to the tree and to which node of the tree it should be connected. Of course, the cube base is decision on the values of the Laplacian at the vertices. In this way, as you can see, the result is a tree that successfully spans the valleys of the Laplacian, and even the one that was merely visible from the heat map. However, the problem now is that our spanning tree covers the entire mesh. So what we need is a criterion to determine which branches should we keep and which ones should we prune. To do this, we remember that the geodesic distance field is non-differentiable at the cut locus, and this makes its gradient to break while approaching the cut locus. On the other hand, it is well known that such field is moot anywhere but at the cut locus. So this means that if we take two vertices connected by an edge away from the cut locus, then the gradient should smoothly vary when passing from one to the other. For this reason, for each node in the tree, we compute the maximum angle that the gradient at such node forms with the gradients at the vertices of its one ring. And we decide to remove that node from the tree if such angle is lower than a given threshold theta. In this way, we are somehow measuring the discontinuity of the gradient and pruning from the tree those nodes at which the gradient is continuous. Furthermore, note that theta is the unique parameter our method depends on and that it is tunable in real time. In this slide, we show two examples of the filtering technique we have just described, applied with the two different choices of theta. On the left, you see that by setting theta equals to 0 degrees, the vast majority of the branches are gone, but there are some of them which clearly do not belong to the cut locus that are still there. On the other hand, by increasing theta to 3 degrees, we obtain a much cleaner result, although as you can see, we are losing a piece of cut locus, namely the one in the inner loop. Note that it is not the case that the portion of the spanning tree we are missing is the one that spans the less deep valley of the Laplacian we have seen from the heat map. In the paper, we give further details about why this happened. So as we have just seen, after the filtering procedure, we obtain a fairly clean result, apart from those short branches that you see and the fact that we have lost a portion of the cut locus. Although in this case, the latter problem can be solved by recovering the correct homology of our approximation. In fact, property 3 implies that the cut locus of every point on a one-genus surface should contain exactly 2 cycles, but by definition, our tree, of course, doesn't. So we need a way to form those loops. We do that by applying a variation of the greedy homotopy basis algorithm proposed by Ericsson and colleagues in 2005. We start by expanding the pruned tree you see in the slide, although this time, rather than the Laplacian, as priority function, we use the geodesic distance field based at the source x. And once this tree is fully expanded, the result looks like this. Note how a different choice of the priority function clearly affects the direction towards which the tree is expanded. In the following, I will call such tree the primal tree. We define another tree now, this time rooted at the source x, and defined on the dual of the edges that do not belong to the primal tree. For this reason, I will call this tree the dual tree or the cotree. Note also that this time we use minus dx as priority function, and in a moment I will spend a few words about both of these two choices we have just made. Once the dual tree is fully expanded, the result looks like this. And to fix ideas, we can look at the close-up. In red, we have the primal tree defined on the edges and the vertices of the mesh, and in blue, we have the dual one, which nodes are the triangles of the mesh, and the rule is that the two adjacent triangles are connected if the edge they have in common does not belong to the primal tree. After the full expansion of the dual tree, there will be exactly 2 edges that are covered by neither the primal tree nor the dual tree, and these 2 edges will be called the generators of the homology. In the close-up, we depict one of these generators in gray. Concerning the choices we have made about the two priority functions, in the paper we explain how such choices make the generators we have just found to be as close as possible to the cut locus. However, it may happen that some endpoints of these generators do not belong to the pruned tree we started with, which was our approximation of the cut locus. To understand why this is a problem, consider the example in the close-up. It is clear that if we add only the green edge to our pruned tree, we are not closing any loop, since the edges in the black circle have been added during the recovering of the homology. So we solve this problem by climbing the branches of the primal tree until we find a node belonging to the pruned one. And by doing this, as you can see in the slide, we are both reconstructing the branch we have lost during the filtering procedure and at the same time recovering the correct homology. And in this slide, we have the final result obtained with our algorithm. So to resume, we have applied a filtering procedure with theta equals to 3 degrees. We have recovered the correct homology of our approximation. Then we have cut all the short branches, and since by property 4 we know that the cut locus is piecewise smooth, we have applied a gradient-driven tangential smoothing. For the sake of brevity, I will skip the details about the last two steps, but of course they can be found in the paper. Concerning validation, note that there are just few cases in which the analytical expression of the cut locus is known. One of them is the torus, and the result is due to Gravensen et al. In 2005. By comparing the results obtained with our method with the ones shown in that paper, we obtain a fairly evidence of the correctness of our algorithm. Furthermore, we have also made the comparison with the algorithm proposed by Del et al., which is proved to converge to the exact cut locus. And as you can see from the slide, the result we obtain is absolutely consistent with the one showed by the authors. We are now ready to present some results. Our algorithm managed to compute the cut locus of points belonging to meshes with a lot of sharp features, such as the one in the slide. In details, note how in this case we are able to detect the presence of points belonging to the cut locus that are aligned along the sharp edges of the hierarchy. On meshes with many fine details, the cut locus could consist in a lot of weak branches due to the vastness of little bump of the geometry. Although by properly tuning the threshold theta, we can obtain a result that retains only the main branches of the cut locus, such as in the examples reported in the slide. Moreover, even on homogeneous surfaces like this one, our method reconstructs the correct homology by closing all the needed loops. In addition, note that all the cut loci we have shown so far has been computed in seconds by our algorithm, while state-of-the-art method would take hours to present the same results. In fact, if we consider only the timings relative to the computation of the spanning tree and eventually the homology, we see that our algorithm is not only fast, but it also scales very well to large meshes. In the case of surfaces with genus greater than 0, we further note that although comparable, the time needed to compute the homology is always greater than the one needed to compute the spanning tree. This, of course, makes a lot of sense since, as we have seen before, to recover the homology, we need to expand an existing spanning tree and then build another one from scratch. It is worth pointing out that all the cut loci shown so far has been computed using the exact polyhedral metric to measure geodesic distances. In fact, such method leads to better results in terms of accuracy. However, in the paper, you can find comparisons between the results obtained with the HIT method and a graph-based approach. I will not enter the details, but essentially, what makes a method that computes geodesic distances suited for our algorithm is related to the neatness of the Laplacian valleys it produces. Overall, we found that the loss of accuracy using the other two methods was not such as to prevent their use in most applications. Before concluding, let us talk about the limitations of our approach. Since our algorithm heavily depends on the accuracy with which we estimate differential quantities, Irregular or coarse tessellation may affect the computation of the cut locus. For example, on the right, you see how the same values of theta lead to more and more accurate result as the number of triangles with which the same shape has been tessellated increases. In the paper, we also describe how irregular tessellation may affect the computation of the cut locus. In conclusion, we have presented a fast, robust, and scalable algorithm that computes the cut locus on meshes with hygienious, sharp features and fine details. Moreover, our implementation just depends on one parameter which can be tuned in real time by the user. And here you can find the link to the repository with the implementation of our algorithm. And with this, I will close and thank you for your attention.